controller, analog inputs, AIs, or variable signal inputs to our controllers, and AOs, analog outputs, or variable outputs from our controller. 0 to 10 volts, 4 to 20 milliamps. We vary the signal output to vary a motor capacity or position or valve position. We take a variable input from a temperature sensor or some other type of sensor. We went through some of the hardwired points on this drawing. Those weren't here last week. We talked about, mainly we went through all the hardwired safeties. The differential pressure transmitter, it's a high static. It's designed to protect the air handling unit from overexpanding. Went through the smoke detectors that are wired back through the fire alarm system. We went through some of the damper operations, how the fan starts. The dampers are interrelated through programming so that the dampers are open before the fan starts. Differential pressure transmitter here is located probably up at our control cabinet with a field probe to maintain pressure in the duct. So we got back, went through the sequence of operation, which everybody's got a copy of. We're not going to flip back and forth anymore. What we're doing is kind of going through a sequence of operation and looking at the components in the air handling unit that are required to accomplish that sequence of operation. We're not really going to get into a lot of programming. We're not going to get into some hardware, now a lot of hardware. We'll look at some wiring diagrams, but the intent of this is just to talk about control concepts and how they apply to the field devices. It's a different training session to get into some of the programming. So last week we went down through the varying of static pressure based on damper, VAV box damper positions, and that was to save energy on fan energy. When all your boxes are wide open, you can reduce your static pressure. When all your boxes are completely closed, you increase your static pressure. Or vice, other way around. So now we're down to when the supplier temperature at the minimum set point of 55 degrees most open. We talked about that last week. Constant volume terminal damper position should not be included in the reset schedule. Chauffeur picked up on that last week. Anybody understand why that engineer by erred right there? In a hospital, we have a lot of patient rooms. They're all designed for 6 air changes. That's about 1 CFM square foot. So if you were involved in some of the earlier training, we determined that 1 CFM a square foot is about an average load in a space without a lot of glass. Interior spaces are about 0.7. Exterior spaces range from 1 CFM to maybe 2 CFM, depending on west exposure, east exposure, north exposure. So if the patient room is at 6 air changes all the time, nothing's really varying. And if it's designed as a constant volume box, which it might be more than 6 air changes, but 6 air changes might be the max and the minimum. So we got all our boxes out there that are at a constant volume position. So they're not really responding to a mostly closed position. They're never going to go closed. So you probably want to monitor some of these constant volume boxes, making sure that as we vary the pressure in the duct, so the ones that are varying, and looking at damper positions of the ones that are varying, that we're not starving some of the patient rooms because they have to have 6 air changes. Control band, set point, increment values, set point decrement values, and frequencies shall be adjusted to maintain minimum static pressure and supply air temperature optimization of stable system control. Maximum comfort control. Change the set point of the control loops stabilized within 2% set point. That's programming language. And has to do with PID loops, how quickly you change them. The graphic, on the air handling unit graphic, provide a button entitled Critical Zone Reset Override. If this button is activated, then the supplier fan should be modulated by the variable frequency drive required to maintain supplier static pressure at 1 inch. That just gives the operator the opportunity to do away with everything we talked about last week as far as resetting boxes. He's going to try to maintain 1 inch all the time. Why would you do that, Thomas? You're not confident of it in your own?
Not confident in the controls.
Yeah.
Or if they find that, several boxes are constantly wide open and it's, screwing up that reset, or,
Yeah.
they just forget it, and just go on in and save it.
Okay, so this is about where we stopped last week, or Tuesday, and we're going to go into the chill water valve, which is, there's the chill water coil, there's the chill water valve. You can see we've got a valve, we've got a point labeled there for an analog output. We've got a temperature sensor here that's just monitoring chill water return temperature, and we'll look at the sequence to see if that has any bearing. And that would be an analog input into our controller. If you look at the next page, chill water valve shall be modulated in sequence with the preheat control valve as required to maintain supplier temperature set point at 55 degrees. In the event of a low limit alarm, the chill water valve shall be fully open. So we talked about that last week, the low limit, right here, this low temperature detection device right here. So it's part of that device right there is a switch. It's hardwired to the drive. So when that switch makes that low temperature set at 40 degrees right there, it goes through the process of stopping the fan. So, but we're also monitoring right here with a point. So that through that point right there, we can go through software. We can probably still pick it up from the drive. But from that point right there, we'll monitor it. And if we see that if the switch makes it 40 degrees, then we can go through the process of programming to open that valve 100%. The reason for that is you get full flow through that coil, less likely to freeze the coil. Okay, so we're looking at a discharge temperature sensor right there, which is an analog input into our controller. We're always monitoring the duct supply temperature. So back through the controller, we're telling that valve to modulate, maintain that temperature right there. Okay, humidifier. See the humidifier?
Yeah,
Right there. Looks like an electric humidifier. Humidifier should be modulated to maintain return air humidity set point at 40 degrees. So there's our humidity sensor in the return duct. And that's return air duct. We got a smoke detector, we got a humidity sensor, and a temperature sensor. So we're going to monitor that system. We're going to try to maintain 40% by enabling this humidifier. We got a still can't read that.
It's a humidifier enabled.
E, enable, S, status. What's the A?
That's an alarm down there. The S is probably the signal.
Signal 2. Well, I'm sure that we'd actually take control of that humidifier, but we may be. This is an electric humidifier.
If we're going to maintain the return air humidity, we're going to have to be controlling the output.
Yeah, so we're not we didn't take this wire straight into the humidifier. The humidifier is probably capable of controlling itself. So we've got a enable device to turn it on and off. We've got a signal device, which this is going to be a digital output, on and off. This is a signal device, so it's going to be an analog output. It varies the signal to this humidifier based on what this is telling us right here. And then we've got an alarm, so a digital output back to our controller for an alarm point. Now the humidifier high limit says HTE, maybe what he's using them.
Sometimes, some engineers call for it to be a transmitter,
Yeah.
and we just vary the signal to keep it below a certain level.
Yeah, that could be just a make an on-off switch type of sensor. It's a transmitter, so it's actually telling us what the humidity is. So there's the high limit. We've got return, outside air mixing. So after the mixed air, we get sensing the high humidity right there. What the high humidity does, that will probably tell this enable to close for this signal to set the signal to 0. And that's to prevent raining inside the duct. Preheat coil with integral face and bypass. There's the preheat coil. We've got a heating valve. It's hot water. And those represent dampers. There's a damper actuator right there. We've got a point to control the damper actuator. We've got a point to control the valve. We've got temperature right here. So the preheat control valves will be modulated in sequence with a chill water valve to maintain supply air temperature at a set point when the mixed air temperature is above 40 degrees. So mixed air temperature, I guess, is that one? We got it after the preheat coil. That's not right. Because the preheat coil, I mean, you're going to have constant fighting back and forth right there. So to truly do what the engineer is asking us to do, this temperature transmitter right here should be truly in the mixed air before everything else is happening, so we can truly know what the mixed air temperature is. We got return air coming back at 70, 72 degrees. You got outside air in the wintertime that could be coming in at 10 degrees, mixing with that 70 degrees. Depending on the volume of outside air, we haven't talked about that, there's the airflow measuring station. And there'll be a damper behind here associated with that to control the amount of outside air. We hadn't talked about that yet, we haven't got to it in the sequence. But that device right there needs to be right here, or we need to add a device right here to really give us mixed air temperature is what the engineer is asking for. So when the mixed air temperature is below 39 degrees, the preheat valve should be fully open, this device right here. And again, the reason he wants to go fully open is to protect that coil. We have constant water flow through those tubes. It's less likely to freeze. And even though this is a hot water coil, as long as we can get water flow through it, it's less likely to freeze. When the mixed air temperature is below 39, the preheat valve is going to go full open, and the base and bypass dampers should modulate to maintain the supply air temperature. So we've got this thing going wide open, so we could be generating 100-degree air, but we want to generate 55-degree air out of the space because this is a cooling only variable volume application, meaning that all the heating is done out at the air handling or out at the VAV boxes. So we're still wanting to maintain 55 degrees right here all the time. So even though this valve is wide open, we take these dampers and modulate them around. This is not really drawn correctly. Probably what the air handling unit looks like. I've got a coil, and I've got 2 sets of dampers. So this is the air handling unit. Probably, we talked about earlier, base velocities on coils. We talked about cooling coils because of the moisture capability of carrying over. We want 500 feet per minute. Okay, so probably in that air handling unit, from there to there, a coil that tall gives us 500 feet per minute. But in a heating coil that's sensible only and has no condensation, we can go to 800 feet per minute. So right there, I don't have to modify my air handling unit at all. All I do is put a shorter coil in there. It's about 2/3 as tall as the cooling coil, and I put a face and a bypass damper. And these dampers probably operate opposite each other, so it could be one jack shaft and one actuator. Because one is opening while the other one's closing. So this is the bypass right here. inside that air handling unit. So it's not drawn truly correct right here, because this should actually be two sets of dampers, and this coil is a little smaller than the actual duct. So that's how you do it. And the reason this is such a small area compared to this is I have no pressure drop right here. So I've got some kind of pressure drop across that coil, so I can do much less area, probably 20% of the area here, because it's free air. You know, it end up probably equaling the pressure loss, because I've got all my air coming down here, then I've got to force it through that opening right there. Well, the manufacturer designs that opening to be probably about the same pressure loss as that coil. So we got to modulate. What happens is you close this damper, you open this damper, or mixed, we start closing, we start opening, so that by the time you get past that coil, that you get a mixed air temperature of 55. So we might have 110 coming off the coil and 10 degrees going through the bypass, mixing to get 55. Which, again, you're going to have some stratification inside here, so depending on where that temperature sensor is, we might want to use this temperature sensor to control here, and again, we just move here to get the mixed air. Because you want that air to mix before you get to where you're going to be monitoring it right here. In the event that the temperature low limit alarm, the pre-coil valve should be fully open to the coil, and base bypass should be fully open to the coil. Read that again. In the event of a temperature low limit alarm, the preheat valve shall be fully open to the coil, and the base bypass dampers shall be full open to the coil. Meaning that we're not getting enough flow to heat the air, so we want to go all air through the coil, no air through the bypass. Temperature low limit alarm shall be generated by the EMS. So we've got that device right there. And we said Tuesday, you know, that's hardwired to the drive. We're also monitoring it, so we're picking up the temperature. Filters. The DDC panel should monitor the filter loading. Well, there's a set of filters right there, and there's a differential pressure switch. So that would be a digital input into our device. All that's doing is making and breaking at a certain pressure. So you listen to what he set it up at, no, he didn't listen to the pressure. Probably on a pre-filter, that's going to be a half of an inch to 1 inch. And do we have any final filters? We got final filter right here. So this is like a 30% filter, and that's going to be like a 90% filter. We got a differential pressure switch on that, monitoring that filter. And all it does is tell the guy back at the front end, I need to go change my filters. Outside air. So there's our outside air flow measuring station. There's our outside air damper. We got a signal here that's probably an analog input into our controller, or actually, that's sensing into the controller, and then we're going to control this damper. So the fan opens this damper when it starts, or the system opens the damper when the fan starts. But then we've got a separate actuator here so that we can take control of this damper and always maintain, they specify, here it is right here, 4,900 CFM of outside air. So this is some type of device. It could be a pitot tube, it could be an electric element that's sensing temperature and velocity, converting it to airflow. Some type of device that's always giving us an airflow measurement. So through the programming, we'll modulate this damper constantly to maintain a certain airflow right there. The outside air damper should be modulated to maintain specified scheduled outside air. The outside air airflow set point should be reset to maintain a positive building pressure sensed by the building pressure sensor. So again, that tells us that he wants to maintain 4,900 CFM, but if the building starts to go negative, then we're going to open that outside air damper even more. The building pressure sensor is common to air unit 2 and 3, so I'm not sure we actually show it on this diagram. We're not showing a building, but it would be a differential pressure setup very similar to this right here that's common for the whole building. Probably on one of the first 4 lobbies, entrance lobbies. And again, that's just an input into our system. We're monitoring that pressure. So if the building starts to go negative, probably on both the air handling units 1 and 2, or 2 and 3, we would start opening that damper to maintain pressure. He doesn't say anything. If we open that damper, again, we're mixing air, so it's summertime, we're mixing air. Let's say this is 72 degrees, and that's 98 degrees. We could have a mixed air temperature here of a higher set point than what the intended coil could handle. So there's nothing in here to reverse that situation if we can't maintain 55 degrees out here. Engineers forgot something. It should be just like you had the damper positions going up and a way to go backwards. You should have an override here. Probably we'll go ahead and do it. We can't maintain 55. We're going to drop that back down to 4,900 and let the building be negative. Or send an alarm. So someone's got to address the problem. Okay. So that's a typical air handling unit. Next week we're going to add an economizer section back here and an exhaust fans. Talk about that. But the intent right here is to take every one of these devices, and if we talked about every one of these devices, we talked about the outside air damper and its electric actuator, the airflow measuring station, the filter differential pressure, return air dampers, return air temperature sensor. Obviously, what we're doing is monitoring that temperature. We're not really doing anything with it. Humidity sensors controlling the humidifier. Another smoke detector right here on the return, just like on the supply. These devices, we're not monitoring. We're not monitoring the smoke detectors. But that goes back to the fire alarm system. And then we're not showing a pickup for the fire alarm system right here only.
Probably a wire diagram
To shut down. So there'll be some type of relay set out here by the fire alarm people that we connect to that relay and we go through our shutdown process. Let's see. High humidity. I think that's high humidity. 95%. There it is, it's set right there. So he's got that humidity sensor set at 95%, which good thing it's upstream from the cooling coil, because downstream of the cooling coil will be the 100% humidity most of the time, because it's just saturated airflow. Low temperature detector, protection device, variable frequency drive, the alarm, the proof that its status, it tells us it's on. Let's say drive fault, and speed control. So there's where we're actually telling them to drive a particular speed. Differential pressure switch, high limit, that's a safety device. Monitoring temperature, another smoke detector, filter switch. Discharge dampers. I think these are smoke dampers.
Probably.
And the differential pressure pickup outstream the duct. So we talked about a complete air handling unit and the sequence of operation. There's the fire alarm monitoring right there. So building fire alarm relay, that's supplied by the fire alarm folks. 2 building fire alarm control. So when that relay, that coil makes, closes that switch, we hook that up to the drive. Actually, that's a point. That's not a hardware point, is it?
Yeah, right there, it's showing the
So we're actually taking that probably should be hardwired to the drive. We're taking it up as a point into our system and then going through the shutdown process. There's our cabinet in the air handling unit. We got a controller. We got some expansion blocks, 2 expansion blocks. This particular controller has a certain amount of points available on it, right there. So there's our digital inputs. There's our analog outputs. There's our digital outputs. Devices that we're controlling on and off, and devices that we're controlling with a variable signal. and the on-off signals that we're getting back into the control. And here's our analog inputs. These are coming from temperature sensors. These are power supplies right here. Some of these devices actually have to be separate 20-volt power supply, 24-volt power supply. So we're taking power out with, why is that, Thomas, why does that temperature have a separate power supply?
They usually differential pressure transducers. If it's a 4 to 20 milliamp input,
Yeah.
we're gonna send 26 volts out and look for a certain milliamp signal to come back. If it's a thermistor, we won't go up to that 24 volts. It just goes to the two terminals.
Okay, so all these are transmitters, and there's our differential pressure right there.
And let's see the very bottom one there, TTE4, it's just wired straight to the two terminals.
Yeah. Okay. That's what the face of that controller looks like. The points that we're connecting to it, they're all going out to the ear. You look at these point names right here, they respond back up to the same point names that are listed in each device. So the guy in the field knows that he's labeled here as well. That panel has, like I said, has a certain number of points. We got an air handling unit that was loaded that panel up, so we got to go to an expansion block. This is a DI expansion block with DOs. So we'll fill out all the points left on that air handling unit. We put this expansion block here. And then we got another one down below here that's going to have analog devices on it. So these controllers don't have any brains in them. They're just communicating back to the main controller. These are just points that we're picking up. So there's our AIs, our signals in, and our control points going out. There's the sequence. What this is right here is a schedule of all those devices. AE is a DEPRA, is an actuator. What do we call it, an AE?
Everything is either something electric or something pneumatic.
So it's actuator electric. Okay. There's the model number, manufacturer. There's a cut sheet that you can see it, and a description of it. That it's modulating, it's 24 volt, it's plenum rated. Differential pressure switch, differential pressure, or it's a differential pressure transmitter.
A transmitter electric as opposed to a pneumatic transmitter.
Right. In switch, expansion blocks. Is that expansion block? What is it? EXP.
Expansion.
Yeah, analog expansion block point. There's our humidity sensor, our low limits, and it's just classified as a thermostat. RE is a relay electric. What is it? Various sockets.
That's just the socket.
Socket for the relay?
Yeah.
I guess that's mounted in our panel on the back plane. We got a place to plug in the relay. Got a sensing probe. These are some of those probes that are mounted in the duct or in the ceiling, or probably mounted in the duct right here. Temperature sensors, temperature transmitters, temperature transmitter electric valves. We got a separate valve schedule. We got a transformer in that panel to power up all our devices. Okay, then we got a very similar air handling unit here. This one is safeties on that VAB. All we had was a wiring diagram handy for the fire alarm shutdown. So does that give everybody a sense of how you apply the controls to an air handling unit? That was a question.
Yes, Chief, you mentioned that on their low limit, that can be hardwired directly to the drive? Is that common, or does that normally go through the control sequence?
Well, the safest way is hardwired to the drive. But what we're doing, like I said, I was looking for the wiring diagram for the drive, which probably shows that temperature detector is wired in series with the high static, meaning that you got a little. So I've got a high static, and then my wiring just goes on over here to another switch that is a low temperature detector. Then I had a smoke detector. Well,
Fire alarm.
fire alarm relay was wired up separately, but it could be another relay right here. That could be the fire alarm relay. And that goes back to points on the drive. So that when the drive starts up, it starts looking at this signal. And all these have to be closed or the drive won't start. If any one of them opens, then my circuit's open and the drive stops. So that's what I call hardwired. And then also on this device, we've got an analog input point where we're monitoring the temperature as well. I think that's what they were doing. I think I saw a point associated with that.
It's a digital.
So this could be a very simple device, or it could be a little bit more complicated device where we could actually monitor the temperature as well. And that's the wiring diagram I was actually looking for, but it's basically going to look something like that right there. It's also probably has the start stop in there. And, any other questions on a typical air handling unit, or any we've got cut sheets, and I might hand out some cut sheets on some of these devices just so you can see what they look like. It's associated to temperature detector versus a temperature transmitter, or damper actuator, what it looks like. But what else can I tell you about an air handling unit? What are you wanting to know? Okay, that's all I got for today. Like I said, next time we'll